All right, everybody, we'll take a look at inverses and derivatives of inverse functions in section 5.3 here, okay? So let's remember something about inverses, okay? Basically, for any relation AB, in a relation is just a set of points. So for any point A comma B, the inverse is, well, what do we do to find inverses? We flip x and y, so the inverse would be b comma a, okay? So kind of a quick reminder that if you have a point, to find the inverse, you flip the x and the y. That's basically what's going on here. Okay. Algebraically, when we do that, we're basically going to replace x and y in the equations with one another, and you'll see an example of that coming up. Okay, and geometrically, inverses are reflections over the line y equals x. Okay, so here's x and y axis here. If I have something like y equals x squared. If I reflect that over the line y equals x, we get the inverse, which would look like this in this case. Okay, and that would actually be y equals plus or minus the square root of x. Okay, but in any event, inverses, we're flipping the x and y coordinates. Geometrically, we're looking at reflections over the line y equals x. Okay, so let's dig a little deeper into some of this stuff just as a reminder here. So for example, let's take a look at f of x equals x squared. Let's find the inverse. Okay, so basically the idea is to do it algebraically, we flip x and y. Now there's no y here, but what we can do is we can replace f of x with y, because that's what f of x represents, is the y value, okay? Now to find the inverse, we flip the x and y in the equation. So y becomes x becomes y, and we get that, okay? X equals y squared, which is your sideways parabola. That's what's up there in green, by the way, okay? Typically what we do, though, now is we get y by itself. To do that, we would have to take the square root of both sides. Don't forget your plus or minus. And so we get plus or minus radical x equals y, okay? And there's the inverse. Now, what I'm trying to be careful not to do is call this an inverse function. Some functions that we start with, like x squared, that pink one, that's indeed a function. It passes the vertical line test. All right, but the inverse, okay, notice is not a function. That does not pass the vertical line test, that green curve, okay? Some functions will have inverses that are also functions. Some won't. Okay, we'll talk a little bit more about that in a few minutes. Okay, but again, just algebraically as a reminder, that's how we find inverses. Replace x with y with x, and then get y by itself again, and there's your inverse. Okay. Let's take a look at another example. Suppose we have y equals 2x minus 1 over x plus 3. We're going to find the inverse relation. Okay, and let's also do the following. State the domain and range of both original and inverse relations. Okay, back up here, just take a quick look at this. If we look at the original y equaled x squared, what do you notice about the domain of the pink function? It's going to go left and right forever, so the domain is all reals, okay? The range of the pink function goes from 0, closed at 0, up to infinity, right? It never dips below the x-axis. It does touch it, though. Now, if we look at the inverse relation, that was y equals plus or minus radical x, or x equals y squared, whichever, okay? Well, look at the domain and range of that, okay? If you look at the domain of the green function, that actually just goes from 0 to infinity. And here, the range, the green one's going to go up and down forever, so that's all reals. But now compare these things. I mean, what do you notice about the domain of the original and the range of the original? They're the same. What do you notice about the range of the original and the domain of the inverse, right? They're the same. So like I said, domain of original and range of inverse, those are the same. And those two guys are the same, okay? Y, well, we're flipping the x and y, right? Domain originally goes with x. When we flip x and y, it now goes with the y, right? And vice versa. So that's, kind of the relationship. If you know the domain and range of one relation, you know the domain and range of its inverse, okay? So like as we look at this problem here, find the inverse relation, state the domain and range of both. Well, let's start by doing that. Let's do the domain of the original. And as I look at this rational function, okay, there's only one x value that's not included in the domain, and that's the one that makes the denominator 0, right? So that's at x equals -3. So, I could write it as, the domain is going to be -infinity to -3, and then again, -3 up to infinity. Basically, we're only excluding -3. That's one way of writing that. Set builder notation, all x such that x does not equal -3. That's sufficient as well. Okay, range of the original. Well, again, there's only one y value this isn't going to touch, and it's a rational function, so we should be thinking there are going to be horizontal asymptotes here. If we take the limit as x goes to infinity of this thing, we should pretty quickly see that that's going to equal 2. So we have a horizontal asymptote at y equals 2. So that's the only value in the range we're not going to touch. So the y values will go from -infinity to 2, and then again from 2 to infinity, or in set builder y such that y does not equal 2. Okay? So there's the domain and range of the original. But what that means now is that we have the domain and the range of the inverse, okay? So, and we'll verify it after we find the inverse, but look, here's my prediction. I'm going to say the domain of the inverse. Well, what was the range of the original? That was y not equal to 2, so I'm going to say the domain of the inverse is basically going to be the same for that, but I'm going to use the letter x. It's going to be x such that x does not equal 2. And for the range of the inverse, I'm going to look at the domain of the original, which basically said all x such that x is not -3. So that tells me in this case then the range is going to be all y such that y does not equal -3. All right, so that's my prediction over here on the side. We'll see if it holds up after finding the inverse, okay? So look, up top we have y equals 2x minus 1 over x plus 3. So to find the inverse, we flip the x and the y. So x by itself on the left, and now I sub in y wherever I had the letter x. Okay, so x equals 2y minus 1 over y plus 3. Now, if you think you can get the letter y all by itself here in terms of x, pause it and see if you can do it on your own with the algebra. But if not, hang tight and we'll go through it together. Okay, so the first step that I would do is actually multiply both sides by y plus 3. Get that out of the denominator. Now I'm going to distribute the x. All right, and ultimately I want to get y by itself. So I'm going to get all the y's on one side of the equation together. And so I'm going to bring the 2y over to the left. So I'm going to subtract the 2y. And then I'm going to subtract the 3x to the right-hand side. I'm just going to write it like that, okay? So basically what I did was I got the y terms on the left, the stuff that does not have y in it on the right. And now what I can do is actually factor out the y on the left-hand side. And then we'll be able to isolate that by dividing the quantity through. Okay, so with these rational functions, you just got to play around with the algebra a little bit, and you get y by itself, but there's now our inverse, okay? If you want, you could factor the negative out of the numerator. Sometimes it might look something like that. Okay, but whatever, okay? There's your inverse relation here, okay? I believe this does end up being a function. But let's check the prediction here. What's the domain of this thing? I mean, think about it. What's the only value x cannot equal here? That looks like positive 2. And what was the prediction? Well, domain would be x not equal to 2, right? Because that was the range of the original. If we take the limit as x goes to infinity here, we have -3 over 1 is our asymptote. That's -3. That was exactly what we figured it was going to be by the domain of the original. Okay, so any event, you'll see, I think, a question like this on your homework. Okay, so give that a try and let me know if you need help. All right, now moving on. In terms of going back to talking about, if a function has an inverse that is a function. Okay, let's talk about that. A function has an inverse that is also a function if the function is 1 to 1. Okay, what is a 1-to-1 function? You talked about that in Algebra 2. A 1-to-1 function is one where there are no repeating x or y values. Okay, a function has no repeated x values. A 1-to-1 function has no repeated x or y values. It passes both the horizontal and vertical line tests. Okay, and so like if you look up here, that's what we looked at before. You know, the pink one passes the vertical line test. It's going to be a function. But if I get rid of this, look, you know, function, but doesn't pass the horizontal line test, so not a 1-to-1 function. Okay, and so its inverse was not a relation, as we saw a little while ago. Okay. Another way to determine if something is going to pass the vertical line test, if you think about it a little bit geometrically, well, it basically means that they're strictly increasing or decreasing. Okay, you know, if you come back to this and you only focus on of the pink curve, if you only focus on this portion of it, that portion is strictly increasing. That portion in and of itself would have an inverse that's also a function. Okay, so in any event, that, you know, if we're strictly increasing, it means we're never going to hit. We're never going to hit the same x or y value twice. Okay, no repeated x or y values, or if, you know, vice versa. If we're strictly decreasing, as we are in just this region, there's no way we're going to have the same x or y values twice. So that's going to guarantee something's 1-to-1 if the whole function itself is strictly increasing or decreasing. Okay, and there's a fancy word for that that's called monotonic. Okay, these are 1-to-1 functions. Okay, an example would be like, you know, f of x equals x cubed. If we were to graph that, it would look something like this. Okay, and that's what we call a strictly increasing function. Okay, there's not going to be any repeated x or y values. It's going to pass both the vertical and horizontal line test. Its inverse would also be a function. Okay, so that's the idea here. All right. All right, so a little bit of review of inverses. Now let's get into the calculus of this stuff, where we're going to look at taking derivatives of inverse functions, okay? Okay, so let's start with an example. Suppose I say, look, if f of x is x squared on the interval 0, infinity. Okay, so we're just restricting x squared to that interval. And the reason why is if we only look at this part now, it's strictly increasing. Okay, so if f of x equals x squared on 0, infinity, find f inverse prime of 9. Okay, f inverse prime of 9 is how I say that. Now, this is inverse function notation. It looks like an exponent of -1. When it's above a function notation like that in f, it typically represents the inverse. Okay, so you got to kind of understand that. That's inverse, f inverse. Okay, f inverse, and then here's the prime of 9. Okay, so that's how we say that. So look, all right, so, you know, we got x squared, great. We want to find the basically, what are we looking for? We're looking for the slope of f inverse at x equals 9. Okay, that's what we're looking for here. So, you know, we can go ahead and you know, apply what we just learned. Okay, well, we can find the inverse. We can take its derivative. We can then plug in 9. So let's take a look at that. Okay, so f of x is x squared. So again, if I replace f with y, I can do that. And now to take the inverse, x equals y squared. Taking the square root of both sides, I get y equals radical x. And again, because we're restricting our domain here, okay, we're going to only accept the positive here. That's not something I want you to get too bogged down into, but basically here's the square, whoops, didn't mean to erase that. Here's the square root of x function coming through, which is the inverse. Okay, that's the inverse function. And both of those pass the vertical line test here, okay? So I could write it like this. Look, f inverse of x, our inverse function here is radical x. Okay, replace y with f inverse of x notation. Okay, so great. We've got our f inverse function. Now we can go ahead and take its derivative, right? So, okay, f inverse, put it in parentheses, prime of x. So I got to take the derivative of this guy. That's really x to the 1/2. So what do we get? 1/2 x to the negative 1/2. Or 1 over 2 radical x if we want to clean it up. And now, great, I've got the derivative of the inverse function. I can finally plug in 9. F inverse prime of 9, 1 over 2 radical 9 is what? 1 over 2 times 3, 1 over 6. Okay? So again, we found the slope of f inverse at x equals 9 to be 1 over 6. Great. Okay? But we're typically not going to end up going through this kind of process to actually find the slope of the inverse at a certain x value. Some functions actually are very, very difficult to find the inverse of. You know, for example, what if I said something like this, you know, f of x is x to the 7th plus 8x cubed plus 4x minus 2. Find f inverse prime of negative 2, okay? Why is that going to be a hard thing to do? Well, look, I can replace the f with the y, no problem. But now let's find the inverse, right? I want to take the inverse of this thing, so we get x equals y to the 7th plus 8y to the 3rd plus 4y minus 2. And really the trouble here is now trying to solve this 7th degree polynomial of y for y. We're going to try to get y all by itself on one side of the equation with nothing but x's and numbers on the other, right? So I wouldn't even know how to go about that. You might be thinking like, well, let's get all the y terms together, and, you know, we can do that. And then, you know, maybe factor out a y. Well, that's fine. You know, but if I get this y by itself, I'm still going to have y's on the other side of the equation. That's not solving for y, right? It's very difficult to solve something like this. It's actually not that hard once you understand how to do it to get the slope of the inverse function, okay? So that's what we're going to talk about now is really there's a relationship between the slope of the original function and the slope of the inverse function. So let's take a look, okay? So look, here I'm going to draw, once again, here's x squared. I'm going to try to do a decent job of this. Okay, there was our original. F of x equals x squared. Get this out of the way, just so. Okay. And then here was our inverse. F inverse equaled radical x. Okay. And now what we were asked to do was find the slope of f inverse at 9, right? So here's, I'll call this 9 right about here. Okay. And what's the square root of 9, by the way? 3. So there's that y value there. So there's the point 9 comma 3. And what we did is we found the slope. The slope there was 1 over 6. That's what we figured out. What I want to actually take a look at is the slope. Let's look at the slope of the original function at not 9, but at x equals 3. Okay, so our original function was f of x equals x squared. You can take the derivative. That's going to be 2x. If I want the slope at 3, we're going to have 2 times 3 is 6. Okay, so I'll call this 3. My graph's not perfect here, but that's okay. I'm just going to try to get that up a little higher, because right here is the point 3 comma 9, so I just want to try to get that to look nice. Okay, but look, now here's, you know, what would we just show? We just showed that the slope there was positive 6, right? Well, think about the relationship, right? These things are inverses. These are reflections over the line y equals x. When we find inverses, we're flipping coordinates. That was the 0.93. This is the 0.39, right? We're flipping those coordinates. Slope is change in y over change in x, right? There's one slope, change in y over change in x. What happens if we flip that over? If we flip the x and the y, change in y over change in x. If we flip that, we get change in x over change in y, right? Well, what happens if we flip 1 over 6 over? We get 6 over 1, which is precisely the slope we got for the inverse, all right, or the original function here. All right, so look, it's a little confusing, okay, but the point is this. Look, if you have two functions that are inverses, there is a relationship between the inverse coordinates and the slopes. The slopes themselves end up being inverses of one another. Okay, so let me kind of like put this all together for you. All right, so here's the idea. Suppose f has an inverse and is continuous at x equals a. Okay, so let's suppose we have a function that has an inverse. Okay, let's assume that f prime of a exists and does not equal 1, or not 0, excuse me. Okay, does not equal 0. Also, on f, we have f of a equals c. What does that mean? It means that if we plug the x value in of a, if we plug x equals a in, we get back a y value c. So we have the point, basically, a comma c on the graph of f. Okay? Well, if this is true, if f has an inverse that's continuous at a, and the derivative of f doesn't equal 0 at a, and we have this point a comma c, then f inverse prime of c exists, and f inverse prime of c equals the reciprocal of the slope of f at that value of a. In other words, 1 over f prime of a. Okay, that's the formula for finding the derivative of an inverse function here. Okay, and again, let me kind of like geometrically try to re-explain it with a more general graph. Okay, using the letters a and c here. So here's our axes. Okay, let's suppose I have some function. I'm going to draw it like this. We'll call it f. Okay, there's my f function. And so the inverse is going to be the reflection through the line y equals x. And so the way I've drawn it's going to look something like this. Here's my f inverse. Okay. And let me pick a point on f. Okay, let me pick a point here. I'll call this a. And the y value there c. And then if I go across and reflect, I get that point. So that's going to be the x value of c, and that'll be the y value of a. Okay, so here's the point c comma a. Here's the point. No, that's c comma a there. And I'm screwing myself up here. A comma c up here. Okay, so there's the inverse points. Okay, on f and f inverse. Okay, so look, if we want the slope of f inverse at c, there's that, right? There's the slope of f inverse at c. So in other words, f inverse prime of c gives me that slope. Okay, it's going to be the reciprocal of that slope right there. Okay, that's the slope of regular f prime of regular f at a. Or in other words, that's f prime of a. They are reciprocals of one another. These slopes are reciprocals. Okay, so a little tricky with all the flipping of the x and y stuff, but let's go through a few examples and then hopefully you get the gist of this, okay? Now, I didn't love the WebAssign problems on this, so in Google Classroom I have attached a separate homework assignment questions 1 through 8, and I've also provided the worked out solutions, okay? So you can take a look at that stuff. But you guys will be responsible for this, so make sure you try the practice problems. But let's try one now. We'll try a few. Hopefully you get the gist, and of course, reach out if you don't, okay? So let's go back to this. Here's some let's do this. F of x equals x to the 7th plus 8x cubed plus 4x minus 2. We're going to let c equal -2. And we're going to find f inverse prime of c. Okay, so what's going on here? Okay, so look, we want the derivative of the inverse of this function at -2 here. So basically here we want f inverse prime of -2, right? C is -2. Okay, but as we saw a moment ago, this is exactly the same polynomial I put up above. You know, how are we going to get the inverse of that? Well, we don't need to. Okay, here's the magic of the formula. All right, so as a reminder, f inverse prime of c equals 1 over f prime of a. So if we can come up with the derivative of the original function and this point called a, then we're going to be able to usually get, you know, what we're looking for here, f inverse prime of c, or -2 in this case. So look, here's the connection back here, right? Here's a very big point, okay? In the inverse, this represents the x value in the inverse. But what does that represent in the original function? It actually represents the y value in the original, okay? And that's what's going on with this point. You know, we have in the original function, crying out loud, my finger hit the wrong spot, so I'm getting frustrated with myself. In the original function, in f, we have the point a comma c. In f inverse, we have the point c comma a. If I want the derivative of f inverse at c, I got to realize that that c value is really the y value in the original. Okay? What a is the x value that goes with that y value in the original. A is the x value that goes with the y value we call c. All right, that's the job. And well, how do we do that then? If we know what the y value of the function is, how do we get the x value? Set original f equal to the c value, solve for x. And that's what we're calling the a value. A is the x value, c is the y value. Okay, so sorry to make it so tedious to get to this point, but this is all the stuff that we have to do. Okay, so to go through the process to find the derivative of the inverse function at a value, we set the original function equal to that value. So in this case, I'm setting f of x equal to -2, and I'm solving. Okay, so here goes. I'm going to take that equation, and I'm going to set it equal to that value. Set f of x equal to c, solve for x, that gives a. Okay, and usually what we do is we solve by inspection. If you had to, you can graph this on your calculator, Desmos, and see where they intersect. But it's usually a pretty easy x value to come up with. Okay, so like as I look at this equation, I can tell pretty quickly if I plug 0 in for x, this equation holds. Okay, so here x equals 0, or in terms of the formula, that's the a value. Okay, so that's step one. Step one, set the function equal to c, solve for x, that's the number a from the formula. Okay, step two now is to just set it up. So look, f inverse prime of -2 is now going to be 1 over f prime of a, which was 0. Okay, so we're going to set up formula, and then I'm going to go ahead and find f prime of x, kind of off on the side here. That should be relatively easy. I'll come up by the function 7x to the 6 plus 24x squared plus 4. All right, and then evaluate f prime of a. So here, f prime of 0 is just going to be 4. All right, sub in. There you go. So there we go. The slope of the inverse of this crazy thing is going to equal 1/4 at -2. All right, that's the gist of this stuff. Okay, let's go through a couple more examples, and it'll become more clear after we do a few together, I think. Okay, so here again, the general rule is going to be find f inverse prime of c for the given f and c. All right, so part A, let's do f of x equals 8x cubed minus 1 and c equals 7. So we want f inverse prime of 7 here. What it's going to be is 1 over f prime, and we got to figure out what this magic number we're calling a is, okay? So how do we do that? We set the original equation equal to c, solve for x. This isn't too bad to solve, but again, I can tell if x is 1, we're going to go ahead and get 7 back. You can add, divide, and take the cube root, and you're going to get x equals 1. So in terms of the formula, we want a equals 1. So 1 over f prime of 1 is what we're looking for. Now we'll go ahead and take f prime. That's not bad here. That's just 24x squared. And I'll evaluate f prime of 1, which is just 24, right? So at the end of the day, the slope of the inverse of 8x cubed minus 1 at 7 is going to be 1 over 24. Once you get used to it, pretty short, sweet problems. Just a few steps, you know. Got to remember to find the x value, do 1 over the derivative, the original function's derivative at that x value. Okay, let's try another one. Let's do f of x equals x minus 4 over x plus 5, c equals negative 4/5. Okay, so in essence we want f inverse prime of negative 4/5. That's going to be 1 over f prime of a. We got to get a. So on the side, set the original f equal to c. And again, play around a little bit, but it looks like if x is 0, we're going to get negative 4/5 back. So we're looking for 1 over f prime of 0. Okay, and it's okay if x is 0. Remember, the rule up here was that the derivative at a can't equal 0, and that's because it shows up in the denominator, okay? But it's okay if x itself is 0 as long as the derivative at a isn't 0. Let's see. A little more effort here. We got to take the derivative of this. Okay. So f prime, proportion rule derivative, the top is 1 times the bottom minus the bottom is 1 times the top over bottom squared. X's are going to cancel, and we're going to end up with positive 9 over x plus 5 squared. Okay, and now evaluate at 0. That's going to be 9 over 5 squared, 9 over 25. Okay, and so we wanted 1 over that. It's going to be 1 over 9 25ths, or in other words, 25 ninths. Okay, so again, find the x value, take the derivative of the original function, plug in that x value, and you're taking the reciprocal of that thing, okay? In terms of ways they sometimes show up on the AP exam, you might see something like this. F of x is x squared plus radical x. G of x is equal to f inverse of x. G of 2 equals 1. Find g prime of 2. Okay, so, you know, we want g prime of 2, right? Well, what does g equal? G equals f inverse, okay? So look, if we want g prime, what are we going to do? We're going to take the derivative. Let's take the derivative of g, so take the derivative of both sides. G prime of x is f inverse prime of x, okay? And so there's our connection. And if we want g prime of 2, we can sub 2 in for x. G prime of 2 equals f inverse prime of 2. And now we see that we have the derivative of the inverse function. We got to set up our formula. So it's going to be 1 over regular f prime of a. So we got to go back and get a, right? Well, look, we have the value 2. We have the f function. Here we can most certainly do what we've been doing. Set the equation for f equal to that x value 2. Solve for x. Try not to work too hard. Again, if you play around, it's not 0 here, but it's not a difficult value to come up with. It's x equals 1, and you can verify that. So that's the idea. We come up with that. Now look, there is another way to come up with that, by the way, and that's this piece of information coupled with this. Look, g and f are inverses. On the graph of g, we have the point 2, we have the point 2, 1. That's what's on g, which is equal to f inverse. So in the graph of f, we'd have the 0.12. There's the y value. There's the x value that goes with it. Same thing we got when we did it algebraically over here. Okay? But again, you know, the more you see this stuff, the more easier it's going to be to pick it out, okay, and to do it. So in any event, now I have 1 over f prime of 1. Well, here I will take the derivative of f. That's going to be what? 2x plus 1/2 x to the negative 1/2, or 1 over 2 radical x. Okay. And from here, what do we get? F prime of 1 is going to be 2 plus 1/2 is 5/2. And so coming back over here, 1 over 5/2 is 2/5. Okay, got the reciprocal back. Okay, so again, that's been on an AP exam before. Here's another one that I've seen. G of x, again, is equal to f inverse of x. If f prime of x is equal to 6x squared plus 2x, and g of 3 equals 1, find g prime of 3. Okay. Find g prime of 3. So g prime of 3, again, let's see. Well, the relationship is, all we know about g really is that g equals f inverse. So taking the derivative, g prime of x equals f inverse prime of x. So g prime of 3 equals f inverse prime of 3. There's the derivative of the inverse function, so 1 over f prime of a. So to get a, we want to set f equal to 3. Problem is here, I didn't give you f, I gave you f prime, okay? But again, with this, we should be able to figure it out. In the graph of g, we have the 0.31. F and g are inverses. So we have 1, 3. Well, there's our a value that goes with the y value of 3. Okay, so here we end up with 1 over f prime of 1. Now I can evaluate f prime of 1 up here. That looks like it's going to be 8. And so 1 over 8 is our answer. Okay, and maybe one more example, and that'll wrap it up. So here, let's suppose f of x is ln of x. Find f inverse prime of 1. Okay. So again, f inverse prime of 1 is going to be 1 over f prime of a. Here we'll take the equation and set it equal to 1. Okay, so ln of what magic number equals 1? Well, you got to know it. ln of e equals 1. So x equals the number e here. So here we're going to get 1 over f prime of e. Come off on the side, figure out f prime. If f of x is ln of x, what's f prime? 1 over x. F prime of e is 1 over e. And I want its reciprocal. 1 over e is just e. And there you have it, folks, okay? So again, a little bit on the technical side. Take some time to digest that, practice the homework problems, check the solutions, and of course, reach out if you have more questions.